Good morning. I'm Nair. I'm a faculty here at SMU, Southern Methodist University in Dallas, with the Light School of Engineering. I'm also the director of SMU AT&T Center for Virtualization. With the name Virtualization, it's very clear. Maybe it'll be clear to you that we do a lot of technology related to virtualization, including cloud computing, cloud communication, cybersecurity, AI, ML, etc. And all those technologies and applications, keep us very close to edge computing and the concept of edge computing. I'm very sure many of you know the concept of edge computing. If not, don't worry. We will be talking about some of the fundamental ideas connected to edge computing, and I will be making an argument for application-specific edge computing. I am very sure all of you heard of term ASIC, that is application-specific ICs, for several decades by now. But many people do not use the term ASIC, application-specific edge computing, but we will make an argument for that. With that, let me move on to the next slide. All right, so what is edge computing? Like I said, there are a lot of misconceptions about edge computing. Many people think edge computing is nothing but desktop computing or a local private cloud. Excuse me. Whereas edge computing, by definition, popular definition, it is cloud principles applied at the network edge close to the user. That is, you're bringing a piece of cloud closer to the customer premise. So the moment we say cloud, we are talking about virtualization, on-demand resources, application programming interface, automated lifecycle management, commodity hardware, etc. All those things applies to edge computing also. So before I go to the next two bullets, I want to talk about a couple of enabling technologies. So what is making this edge kind of important right now? So a couple of technologies which is really making it kind of indispensable are one, cloud computing, of course. Almost every IT asset for people are moving to the cloud now. So that is there. And then SDN, software-defined networks. That is where the actual hardware-software disaggregation is happening. If you really look at the internet of today, we have humongous routers, which constitutes one of the largest distributed computing system in the world. And these routers are humongous in the sense it could be a huge computing element with a lot of intelligence and cost, anything from $500 to $5 million. And telecom companies are spending billions of dollars in terms of refurbishing them on an yearly basis. So what they decided is, with virtualization concept, you can disaggregate the intelligence or the software and the hardware. So what they did is exactly that. They took the intelligence in the routers and put them on the cloud, and we call it the control layer. And then the routers are replaced by commodity switches. That immediately reduces costs, and then because of the centralized intelligence, you can have the whole view of the network, and you can centrally orchestrate different services on the network. And now the networks are going to be the next technology we are going to talk about is network function virtualization. You can virtualize almost every network functions and put them as applications above the control layer. And then, of course, you're all familiar with IoT devices, Internet of Things. Right now, the world is sensorized. We have so many sensors and video cameras and robotic arms, everything in the customer premise, creating or generating a lot of data. So all these different things either are going to demand very low latency or are going to present very large volumes of data. Both these scenarios are quite suitable for an edge workload. So we will talk about that in detail. So on the left side, I talk about the convergence of IT and telecom networks. The moment we talk about the hardware-software disaggregation, that means part of the network is software, which can be done by large IT companies, including Microsoft, Google's, and Amazon's of the world, right? So what is the real difference between a telecom company and an IT company? In fact, the difference is shrinking day by day, and new innovative and immersive applications. Now the IT companies can produce telecom applications. Similarly, a telecom company can produce IT applications. And then because of this, there are so many new immersive applications that are emerging. So one other point I want to make here before I move on to the next slide is edge versus cloud. Right now, if you look at it, around 10 to 15% of the data is now processed outside cloud. What it means is the rest of it is processed inside the cloud. But that trend is slowly changing. The prediction is in next 3 to 4 years or 5 years, more than 80% of the data is going to be processed outside the cloud. Does it mean that when I say outside the cloud, it is going to be on the edge? Does it mean that cloud is going to disappear? No, the cloud and edge are going to be coexisting. They have to. The growth of the cloud is going to be reduced, but the size of the cloud is not going to reduce. Whereas CAGR, the cumulative annual growth rate for edge is predicted to be anywhere from 30 to 40%. Let's move on to the next slide. So what is an edge infrastructure? So if you really look at edge, you are going to look at a piece of cloud coming closer to the customer premise. That's exactly what it is. So in this diagram on the left, you can see there are a lot of endpoint devices, that is customer edge devices. And then there is a protocol translating gateway. And then there is an edge server, and then a local micro data center or near edge for edge data centers. The idea is this. So you have centralized cloud, you have customer premise. In between, you are going to see a continuum of different edge centers or edge devices. The idea is there could be one edge device which is going to be somewhere farther from the customer premise. There could be some edge coming a little bit closer, 10 kilometers closer to the edge. And sometimes there could be an edge server sitting inside the customer premise. But the real difference is, even if it is sitting inside the customer premise, it is going to be serviced or run by a web service provider or telecom service provider. That's the real difference. And on the right side, you can see, just to give an idea of the funneling size reduction when you look at the numbers of devices and the cloud or data centers. You can see billions of devices in the edge devices, and you are talking about the IoT devices. You can see the different types of devices in that diagram. And then when you get to the edge server, it is in millions, and then edge cloud is going to be in thousands, and enterprise hybrid cloud is going to be in hundreds. So that's how the reduction happens. And once again, the real important aspect of edge is going to be used by anybody who is using cloud. At the same time, the workloads are characterized by two major things. One, very high bandwidth. You don't want to use connectivity to your premise to the cloud on a constant basis supporting that much high bandwidth. At that time, you want to terminate those connections as much as possible at the edge. Then very low latency. You do not want to have a real-time application where the control and command has to come from the cloud. It is going to add multiple milliseconds to the latency, which is not going to be acceptable to the application. So who uses edge? Like I said, anybody who uses cloud should be using edge. So if you look at the diagram, this is a diagram from McKinsey. Travel and transport, global energy, retail, healthcare, chemical, agriculture, everybody uses cloud, and because of that, everybody is going to use the edge. So I'm going to use another slide, next slide, where I will characterize these edge workloads. If you look at this, the key aspects here are what on the y-axis, you will see the volume per day per site. And the x-axis, you have application level latency requirements. So when the bandwidth requirement is very high, and the latency, when you move in the positive direction, you are looking at smaller latency. So this area, the top right corner, is where the most activity in edge is going to be happening. At the same time, even when the latency requirement is not there, if the bandwidth requirement is very high, still you can use edge computing. So the regular hyperscale cloud architecture is going to be used in the lower part of this sector. That is, you may not have that much bandwidth requirement. At the same time, latency is not going to be that high either. Now, let's talk about some use cases. So I already talked about the merging concept of IT and telecom. So on the left side, you're talking about the third-party edge applications, or I would say the IT applications. On the right side, you're going to see the operator applications. I'm not going to go through all the use cases, but let me talk about a couple of very important, interesting use cases. One, we already talked about, wherever you have very high bandwidth and very low latency, you have to use edge computing. A very good example is video analytics. In fact, one of the earliest edge applications that were deployed was for video surveillance or the video analytics. I will give you the name. 7-Eleven, for example, use for their security, they use video analytics, and their servers are the processing is done by the edge servers used by them. There are a couple of other scenarios which may not be very clear to people where we can use edge. For example, when the computing power for the service is not quite adequate, you can offload some of the computing needs to the local edge. The very good example I can give you is the electronic billboards. When you see electronic billboards, when you drive through the highway, you can see them displaying different things. I mean, you may just think, okay, it is just a display, somebody's playing it from somewhere. So most of them are connected to the network, and they are doing this display using web browsers. And the computing power for those billboards are not that very high. So what they do is many of the processing that is necessary to render the video and whatever information they are showing, that is going to be offloaded to a local edge. Another good scenario you want to think about is where you don't have good connectivity. Very good example I can give you is Doctors Without Borders, right? They go to different places, Peru or Haiti, or whenever there is some natural disaster or something. At that time, when you go there, there is no connectivity for this group. At the same time, they need to use the, data collection, and they have to have the connectivity among the doctors or the physicians, for visiting and serving the population. At that time, there will be a local network setup, and there will be data collected. And sometimes you need to do some analytics there. Who's going to do it? We don't have any connectivity to the cloud. At that time, you can use an edge server. So that is another good use case. And on the right side, you can see the operator, telecom operators or web service providers using a lot of analytics for security. And then they are running the network function, virtual network functions on the edge. One good example I want to give you with respect to the operator is collecting data and analyzing it for the RANs, the radio access networks. So think about this. You may be using a video streaming service using your mobile phone, and the stream is coming from a central server. Your connectivity is going to be affected by the quality of the wireless connection you have to the wireless gateway. At that time, the server who is streaming the video doesn't have any knowledge of how good your connection is. Whereas if you have an edge who is collecting data about your RAN connection, they can send that intelligence to the server, the streaming server, so that they can do the traffic engineering. Even for the TCP/IP connection, they can adjust the transmission window, etc., so that your experience, the user experience, is going to be adequate. So on the right side, I have put out the specific benefits of edge computing: ultra low latency, very high network throughput, context awareness, because edge is at a certain place. For example, you may be using this connection in downtown area versus in a rural area. Based on that, you can adjust your context and accordingly the performance and the contents, etc. Data filtering, reduction, and compliance, and especially for privacy and things like that. Even you could be in different countries, and based upon your locality, the security or the privacy compliance policies will be different. The system can automatically adjust it, quite transparent to the user. And of course, you can provide security because you are dealing with the security of the edge itself, so that an attacker cannot get into the central cloud. Now, I cannot finish this talk without talking about 5G. 5G is touted as virtual zero latency, gigabit, ultra reliable connection or experience to the user. So how is it possible? So until now, when we talk about different gradations of wireless technology, we have come up to LTE. Now we have full IP connectivity, etc. But what is lacking there? What was lacking there was ultra low latency. I'm going to show you some use cases later where we can use the low latency of 5G. 5G uses millimeter waves, and because of that, we can get sub 10 millisecond latency for the applications. But you can realize this only if the processing can be done at the local edge. So 5G, in spite of all this marketing the telecom companies will do, the key component to 5G success is going to be the local edge. So now I'm going to move a little bit to a standardization of this edge. So if we have the proliferation of this edge, each vendor will be making their own edge. That is not going to work because many users will be using different edges depending on where they are. So ETSI, the European Telecom Standards Institute, they came up with a standardization process, and then they have something called MEC. That is, initially it was called mobile edge computing. That's exactly what I started out in the previous slide. And the next one, they changed it to multi-access edge computing, mainly because now not only does this cover the standards for mobile computing, but also for general IT applications. So the concept is very similar. Let me show you the next slide. This is exactly what is happening with the MEC framework. So if you really look at the network function virtualization, what people do is they have the network infrastructure underneath. On top of it, there is an NFVI, that is a network function virtualization infrastructure. On top of it, they will put the virtual network functions. Now, with MEC, multi-access edge computing, what happens is, in addition to the network functions, they will put mobile edge and other IT applications. All those applications can coexist. They can be orchestrated and managed at that layer. The MEC also popularized many proof of concepts. You can see the list, and these lists are nothing but different successful applications people have built. And I strongly recommend you go to their website so that you can see new applications that are coming up. You can see, I mean, the examples are very similar to the use cases I showed and discussed so far. Now, I just want to talk about some complex use cases. So one of the flagship projects we have at the center is remote robotic surgery on 5G. This is a consummate example for edge computing. So the idea is this: right now, when you look at it, robotic surgery, a surgeon will be sitting in one corner of the room and in front of a console. And then that console is connected to the robot, which can do the surgery, and it is connected through a fiber cable. What we want to do with the 5G is cut that fiber and use 5G. And why did we wait? I mean, why couldn't we use Wi-Fi or for LTE before? The reason is the latency. But for that to work, we need to get an edge closer to the robot, so that even if there is a network latency or failure, the robot can continue the surgery safely. So in conclusion, edge is becoming indispensable, and we visualize a device edge cloud continuum. So where is the application specific stuff? So we already saw for different applications, the requirements are going to be different. And because of that itself, edge is not going to be a general purpose cloud, rather an application specific yet cloud native server. And that's exactly the reason why we call it application specific edge. And the new market dynamics is coming up. You're going to see thousands of edge distributed all over the place, co-owned by different service providers, application providers, etc. And I will stop right there. And then if you have any questions, I'll be happy to answer those questions. Thank you very much.